So, lecture 10. We finished grading the midterms. I think we just posted grades like a few minutes ago. So, find those online. The grade distribution looked like this. So, this is before curving it. I'm going to do curving at the end of the quarter, to compute the final grades. But as it stood, a lot of students did very well, and no one did really terribly, which is pretty good. And the average was about 85. Okay. Does anyone have any questions about the exam?
Will we get them back?
Yeah, you'll get them back. They will be here, I think, before the end of the class. So you'll be able to collect them after class or from office hours. Yeah, and I encourage you to do that so you can compare what you did to the right answers, or at least what I thought. Yeah, so one thing I noticed from the midterm, a common mistake people made in the question was asking about round trip times, like what happens to a TCP connection if the round trip time is increased. And many people said that the TCP window size was controlled by the round trip time, which is not true. The answer I was looking for was that round trip time controls the timeout that's used. I think the reason why I think many of you answered this is because I had a lot of homework questions, or at least 2 homework questions, that asked you a very similar question. It was like, given a certain round trip time, what should the window size be? Right? But that's not like a cause and effect relationship. That is, if there's a certain round trip time and we want to achieve a certain bandwidth, then we would like the window size to be at least a certain size. But what actually controls the window size is congestion control and flow control in TCP. Right? So not the round trip time. Yeah.
But you said project 1.
Yeah, let's just say project 1. Yeah, I guess it's been a long time. Sorry about that. Yeah, that should be project 1 grades posted today. There's project 2 out there. Lucky it. You all get zeros. So obviously, okay, so Friday is the course drop deadline. That's why we're trying to get as many grades back to you since today. And if you think if you're considering dropping because of your grades, talk to me and I'll give you a better idea of what letter grade you'll end up getting based on what your current average is. Because if your average is like a 70 right now, it doesn't mean you're going to get a C minus. Because the average grade is probably like in the 80s, and that's going to probably get bumped up to like a B plus. Anyway, so that's all that. Any other questions? So last lecture, I talked about IP version 6 and shortest path algorithms to sort of lay the foundation for routing algorithms, which we're going to talk about today. And I introduced briefly. Okay, so actually, before I move on to this, there's one other thing I wanted to mention. There was a question last time about whether a NAT can have multiple IP addresses, right? And I said no, but I don't think that's precisely the correct answer. I think it would be possible to build a NAT device that, if you had a router that had multiple public IP addresses, and it was connected to a large private subnet, it would be possible to take connections from the private side and multiplex them across different public IP addresses. And as long as the table that the router is maintaining keeps track of which public IP address, the same way it keeps track of which port is being used on the public side. So there's nothing to prevent a NAT from using multiple public IP addresses. I'm not sure if it's done very commonly in practice. All right, so so I introduced the term LAN for wide area network and LAN for to distinguish between the public internet and private internet, which is an extension of the topic we already introduced with NATs. So I don't think that's too new. It's a pretty simple concept. Then I talked about IP version 6, which uses 128-bit addresses, and one of the reasons IP version 6 was introduced was so that more of the internet could be publicly addressable, because there are only 4 billion IP version 4 addresses. So now that we have more than that number of devices on the internet, probably, or when we hope to get past that number, we want to have a public internet, we need more addresses. And then I showed what the headers look like, and also how IP version 6 and then version 4 can interoperate by tunneling. Even if routers that are deployed right now were built before IP version 6 was even invented, you can still transfer IP version 6 packets through those old routers if you wrap the IP version 6 packets inside an IP version 4 packet and send it to an IP version 6 compatible router on the other end of that connection, where it'll be unpacked and delivered. So then we started talking about routing algorithms, which are the algorithms used to determine the forwarding table at each router. Those tables that determine, this block of IP addresses goes to this link, this other block of IP addresses goes to this other link. And I categorize them as either centralized or distributed. And for a centralized algorithm to work, you have to kind of gather all the global information in one place so that you can solve some sort of a shortest path problem, or otherwise make a decision using all that information. But a distributed algorithm is attractive because you don't have to gather all that information in one place. So to start solving these routing algorithms, we sort of abstracted the network into a weighted graph, where we had vertices or nodes and edges, and every edge had a weight, which was somehow supposed to represent the cost of the edge, which usually would be the delay of transfer between 2 points. Or it could be something else, depending on what your goals are in routing, I guess. But I introduced the Bellman-Ford algorithm for solving the shortest path problem in polynomial time. And one thing I didn't mention is that we need to actually have a clever algorithm to solve the problem, because the naive solution would be to enumerate all the paths and just find the one that has the minimum cost. You can't really do that because there are n factorial different paths possible in the graph, because you can choose any of n nodes as the first point, and n minus 1 for the second, minus 2 for the third. You have to multiply all those different possibilities. It's an exponential number of possibilities. But the Bellman-Ford equation sort of breaks down into a dynamic programming-based recursive solution that lets you solve subproblems that apply to multiple other larger problems. You kind of eliminate this need to do exponential calculations. So today I'm going to talk a little bit more about shortest path algorithms. I'm going to go briefly through Dijkstra's algorithm, and then after that we'll go into how these are really used in practice with routing. Okay? All right, let's get started. So to remind you all of what we spent some time on last week, the Bellman-Ford recursion here is the way you can express the optimal solution to the distance between x and y in terms of the subproblems of this distances between x and all the possible neighbors of v, plus the cost to get from v to the current to the position y in one hop. So the cost of an edge is what c dy represents, and the cost of a path distance dxv is what that represents. So all you have to do basically is consider all the possible nodes you could go through in the last hop before arriving at the final destination, and consider the fastest way to get to that predecessor when you're calculating whether or not you want to use that particular node as the predecessor. And so this basic formula applies to both the several different algorithms for solving the shortest path, whether it's Bellman-Ford that I showed you last time, or Dijkstra's algorithm, which I'll show you this time. Okay, so this I showed you last time. I reworded it a little bit, but it's basically the same. Is that readable? So just as a reminder, what Bellman-Ford does is it goes through I rounds, and every round you calculate the optimal distance to all the nodes from the source using at most I hops. So initially, all you know is that you can get from the source to the source in 0 steps, because that's trivial. But then as you go through, in every round, you look at every single edge in the graph, and you try to determine whether or not that edge has a cost small enough that when you add it to the distance on one end of the edge, you end up with a total path of, you end up with a total cost of the origin, some path to u, v. If this thing together is smaller and what you originally had recorded as the distance to v, that's your new shortest path. And this takes cardinality of v times cardinality of e time. In other words, the number of steps that it takes is the number of vertices, because that's the number of times this loop iterates, times the number of edges, because that's the number of times this loop iterates. Okay, so that's actually a really simple algorithm for shortest path. It's easy to analyze, and we'll see later on that it's easy to implement in a distributed way. Okay, so the, I guess, better algorithm for solving shortest path is Dijkstra's algorithm. It's better in the sense that it's faster. So usually, if you were to Google shortest path, you come up with probably Dijkstra's algorithm in the beginning of the search results or whatever in the Wikipedia page. And it's a little bit more sophisticated, but it uses the same basic idea of the Bellman-Ford equation here. So actually, if you compare the two slides, this part down here is almost the same, and the initialization up here is almost the same, where you initialize the graph such that initially you think that the distance to most of the nodes is infinity, but the distance to the source node is 0, and you kind of try to add more information in rounds using the Bellman-Ford equation. But the way that you move through rounds is different. And in the case of Dijkstra, that's sort of illustrated in the invariant, which is different. So in every round, what you know is that the distance to nodes j, if j was visited, is the shortest path. Otherwise, it's the shortest path using only the nodes that were visited. So what you do is, in every iteration, you add an additional node to this set of nodes that have been visited. And over time, eventually, so initially you examine one node, you visit that node, you end up with the shortest path to that node. Second round, you add another node, and then you'll have, by looking at all the neighbors of that node, all the neighbors of that node and the cost of the edges from there, you'll figure out the shortest path to all of now those two nodes, and so on and so forth, until eventually at the end you have the shortest path. You will visit all the edges, all the nodes, so you'll have the shortest path to all of the destinations. And the advantage of this is that it's faster. Depending on how you implement this line here, which is where you find the next vertex to consider, and because you want to consider the vertex that has currently the minimum distance estimate of the distance from the source to that particular node. If you implement it with a priority queue, that's the ideal thing to do, and the runtime complexity is e plus v log v. But even if you just scan through every single vertex to find the minimum, you still get runtime v squared, which is faster than v times e, because in general e could be v squared. So this is actually, in the worst case, v cubed. Because there could be an edge between every single pair of vertices, which would be v squared edges. Okay, so how many of you already know Dijkstra's algorithm really well? Show of hands. How many of you don't know Dijkstra's algorithm really well? Half and half. Okay, so here's an illustration of Dijkstra's algorithm at work in an animated GIF. So it starts here. So it's calculating the distance from this node, shortest distance from this node to every other node in the graph. In this particular graph, it's using Euclidean distance to weight every edge. So if you see an edge that looks longer, that means the weight is longer. And that's why this illustration is easy to follow. But in every round, it's adding an additional, it's visiting an additional node. So at this point, all these nodes that have lines connecting them, this spanning tree, those are the visited nodes. Eventually, it will visit all the nodes. And at any given point in time, the invariance is that we already have the shortest path to every one of these visited nodes. Okay, so every one of these blue lines represent the shortest paths that we've already calculated. So how does that, to see how that works, you have to look at the beginning. So it started off with the node that was closest to the source. or which was the source itself, so 0. And then it looked at all the edges outbound from the source, and it calculated the distance to those, so then it had the distance, an estimate of the distances to this, 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 and this. And then it looked at the second one, which was this. And at that point, it already knew that it had the shortest path to this node because the logic is a little bit involved, but because the fact that we chose the closest vertex to consider next ensures that we have we're building shortest paths. And then from there, so it considered all the outbound edges from that node to calculate the estimates of the shortest paths, and then it moved to the next closest one, which was this. And at that point, the only thing we really know is that the distance from here to here is minimal, and the distance from here to here is minimal. And just proceeds onward and onward. Okay. I think that might be all I want to say about this. Maybe if we have time at the end, I'll do a paper example or a whiteboard example showing how this actually works. And yeah, but for this algorithm is actually what's used in centralized algorithms for computing the shortest path. Because it's the most efficient algorithm for shortest path, but it's not used in distributed algorithms for shortest path because it's difficult to maintain this sorted list of visited nodes if things are happening in a distributed way. So whereas the much simpler form of the Bellman-Ford algorithm allows you to split up the work without sharing a lot of information more simply. Although in reality, when we parallelize it, we don't really, it's not really the same as the Bellman-Ford algorithm, it just looks like it. Anyway, so I'm going to skip that actually, and do it at the end. Okay, so to compare the two algorithms, just at a very high level, Bellman-Ford is simpler, Dijkstra is more complicated, Bellman-Ford is slower, Dijkstra is faster. Even if we use the simplified version of Dijkstra, where we have E plus V squared, that's still smaller than V times V, because V times E, because E is actually generally could be as high as V squared, although in practice it probably won't be. Bellman-Ford can handle negative cycles. That's not really important for network routing because you're not going to have negative delays. But like I said, Bellman-Ford, because of its simplicity, can be adapted to a distributed implementation. And we'll see that in what's called the distance vector algorithm. And BGP, which is the real algorithm that uses this idea, which is sort of like the glue that holds together the internet at the global level, implements something like Bellman-Ford, okay, which we'll see. Dijkstra's algorithm is the most efficient centralized algorithm, and this is used in what the book calls link state algorithms. A particular example would be OSPF, which is an algorithm run by routers that are kind of all nearby and managed by the same organization. But let's talk a little bit about the distance vector algorithm, which is a distributed implementation of shortest path based on Bellman-Ford. Okay. So remember that, let's just actually do a quick review of the basic version of Bellman-Ford. So the way this works is that, like I said, each round you know the shortest path using at most I hops. So generally, over time, you build, your information propagates to longer distances within the graph, and you consider all the edges in every single round, and just see whether you can use that edge to do what's called a relaxation, which is to make the distance between from the source to the endpoint of that edge smaller by using that edge as the last edge in the path. Okay. So the same basic idea is used in the distance vector algorithm, but because it's distributed, it's maybe a little bit harder to understand and to describe. But basically what you have, just like those other algorithms, you have an estimate of the shortest path at any given time. So the notation I'm using here is d sub x of y is the estimate of the shortest distance from x to y. And in this particular case, we're thinking about a particular node x storing the shortest paths from itself to every other node in the graph. So this is actually a little bit different than the formulation I showed earlier, where there was a single source node, and we were trying to figure out the distance from that one source to all the other nodes. In this case, I mean, it is sort of the same in that we have a source, but the source is different for every actor in the algorithm. Every node in the graph is interested in the shortest path from me to everyone else. That's what the router cares about. Okay? And the router keeps an estimate at each point in time of the distance from itself to everyone else in the network. It's not, just like in those other algorithms, it's going to be grossly inaccurate at first, and over time it'll get more and more accurate. And it'll use a sequence of relaxations to make it more accurate. But basically, so the notation here is that this bold capital D is a vector of distances at this node x. So it's basically just a list of numbers indicating how far away it thinks all of the other nodes in the graph are to itself, right? And when I say it's an estimate, it's an upper bound because it does represent the true path that it's aware of, but initially it's like infinity for most of the neighbors because it doesn't know of any route, or it's 0 for itself. So initially all a node knows is the cost to reach each neighbor. So a node is aware of its surroundings. We assume that every node knows what the weight of the edges are nearby. So here's a node. It knows that this is 3, this is 2, this is 1. But anything outside of this range, it doesn't know anything about. It knows what the total number of edges is, what the total number of nodes are. It knows, for example, that n is 43. There's somehow 43 other neighbors out here. It doesn't know how to get to them. All it knows is what's nearby. Okay? So initially, this particular, if we call this node x, initially we have d sub x, a vector that has values 1, 3, and 2 somewhere in there, corresponding to whatever number of nodes these are. Every node has a number. But then everyone else, all the other nodes are marked as infinity because it doesn't know how to get to them. Okay? Then over time, it's going to fill this in and both lower the estimates it has for nodes. Like these are not, in the end, hopefully we don't have infinity as the distance to any of the nodes because hopefully they're all reachable. These will lower down to what the actual distances are. Okay, so this is all it knows. It initializes it like this, and then the key thing is that it shares information with its neighbors and rounds. So it goes through. First off, it has to send a copy of its distance vectors. A dv distance vector refers to this vector here, which is a list of all distance estimates. It sends it to all of its neighbors, and then it keeps a copy of not just its own distance vector, but the distance vectors of all the neighbors. So this particular node here has 3 neighbors, would have 4 vectors in total, corresponding to each of these, the estimates it has received from all of its neighbors, right? And whenever it gets a distance vector from its neighbor, it is able to recalculate its own distance vector and get a better estimate of it. And after it updates its own distance vector, it then sends its updated version to its neighbors, and then its neighbors update themselves, and so on and so forth. And eventually, by doing this, information propagates through the whole network, and eventually it converges to the shortest path. Okay. So what do I mean by recalculating its own distance vector when it receives a distance vector from a neighbor? So just like in those other algorithms, the Bellman-Ford algorithm and Dijkstra's algorithm, you use the same equation to do relaxations to recalculate distances. So like I said before, initially the distances you have are either the weights of edges that you have measured, or they're infinity if you don't have a direct link. And then when you get an updated set of an updated distance vector from a neighbor, you can basically look through all those values, which are the distances from that neighbor to everyone else in the network, or at least upper bounds on the distances from that neighbor to everyone else in the network, and see whether if you travel from yourself to that neighbor, so that cost of that edge, plus the distance that that neighbor thinks that it, as an upper bound, has to that other third node, if that's lower than your current estimate, then you add that to your distance vector. And if you can basically check to see whether your distance vector changes after you receive an updated vector from a neighbor, and if it does, then that means you need to broadcast your new distance vector to your neighbors and let them recalculate and let the algorithm continue that way. Okay. So basically every node, all it has to do is wait for distance vectors to come from neighbors, or for your local link costs to change. Because actually, we can imagine this being a dynamic network, not a static network. So over time, delays observed between different links nearby could change. Like for example, this could go from 3 to 4, and then that might change the optimal routes. Whenever that you observe a local change or you get new information from a neighbor, you run this calculation to recompute your distance vector, and then you tell your neighbors about it. And that's all that needs to happen. Okay. Questions about that? Okay. Let's see. Yeah, let me make this a little bit more concrete with an example. Okay. So we have a network that looks like, say, this, and we have edges like this. Let's say just like that. Okay, and let's number these guys. Okay, and then now the important thing is that this algorithm is going to run on 6 different nodes. So there's going to be a lot of stuff going on at the same time. Let's just consider what happens at first on one of the nodes. Like let's say node 2. Okay. So initially, node 2 has a distance vector, which is d sub 2. It has 6 values. We need to have labels on these edges so we know what distances to use. And these will be probably based on round trip times that are observed, or some other, like the cost of using a link. These could be whatever you want them to be, but let's just say that these are like 10, 2, 3, 4, 7, 1, and 1. Okay? So initially, the distance vector for 2 in this first position stores the cost from 2 to 1, which is 7. So basically for these 4, we're going to have values, and for everyone else, we're going to have infinity. For 2 itself, we're going to have 0, because we can reach ourselves in 0 steps. For 3, we're going to have 10. For 4, we're going to have 3. For 5, we're going to have 3. And for 6, we're going to have infinity. This is maybe, I happen to choose a node that's very highly connected to start off with. Okay? Make sense? But then, for everyone else is going to have a similar thing. So let's just maybe show one other one. D1 itself is 0 to 2 is 7, 3 infinity, 4 infinity, 5 is 4, and 6 is infinity. Sense? Okay. So, in reality, we want D1 to get, for example, eventually this to know that the distance from 1 to 6 is 5, because it's 4 plus 1, right? But it doesn't know that yet. So these nodes share information with each other as the first step. And so what, I guess we'd have to write all of them out to really know what happens. Which is going to be a lot of work, so I'm not going to do that. But let's do half of that step for the first one. So when D2 goes to recalculate its distances, it'll have D1, and it'll have it'll have all of its neighbors. It'll have 1, 2, 3, 4 different other vectors. Right. So to recalculate the distance to node 1 here, what D2 does is it says it looks for the minimum across every other node of the distance to get to that node plus the cost to get from me to that node plus the estimate that node has of getting from itself to the final destination. So, for example, I can use D2 can use D1 to figure out that it can get this is kind of hard to work out. From myself to this other node plus the cost from that node to whatever final node I want to get to. So if I want to recalculate the distance to node 5, for example, I calculate the minimum of what I currently have for 5, which is 3, or an alternative I can now consider is the cost of myself to 1, which is 7, plus what I just got here, the distance from 1 to 5, which is 4. So 7 plus 4 is 11, which is greater than the 3 I already have, so I did not update this value. Right? So unfortunately, this node doesn't add anything that will help me. If I were to get the distance vector 5, maybe that's the one example that would help. So D5 initially would be 4, 3, infinity for 3, 1 for 4, 0 for 5, and 1 for 6. Okay, when D2 is recomputing the value of D2 sub 6, it can look at whether what the minimum of either infinity or the cost to go from 2 to 5, which is 3, plus D5 sub 6, which is this value, so 3 plus 1 is 4. So eventually, this value here we change to 4. And at the same time, you would also record, along with these things, you'd have a vector that indicates what node was used when calculating as the next hop and calculating that. So here you would store that we actually used node 5 to get to this value of 4, whereas for all the other ones, all we're using is ourself. Okay, and so as far as I can go with this kind of example. Back to slides.
was just wondering like how much like a tree, like the network structure is, because if the network structure, like you'd imagine it's somewhat like a tree, since there wouldn't be that many cycles, since they'd be redundant, there would only be like one path.
Well, there are a lot of cycles in a network because networks actually have multiple connections between other networks for redundancy and also to like distribute the load. So when you're designing a small network, I think you would probably do so without creating loops, like to minimize the number of connections you have to make, basically. So a tree will let you get to every spanning tree will let you get to every node in the network with a minimal cost. You choose a minimal spanning tree, but then you don't have redundancy, and because the system as a whole, like the internet as a whole, is not designed by like one person who's deciding like, okay, let's put a link here to make sure that these two things are connected. The links are kind of built in an ad hoc manner. That means there's redundancy for that reason as well. Yeah. So, but I don't have a like numerical answer to like how much, how close is it to a tree versus not. My guess is that some researchers have measured that in like there's an internet measurement conference where people do measurements of like distances and throughputs and topography of the internet. You might find that kind of information. Okay. So one interesting thing is that the cost of nodes can change, of links can change. So for example, we might have a link that goes from having a certain cost to becoming totally offline if a link breaks. So the cost could go from a certain number to infinity, or it could just get slower or faster, and you want your algorithm to adjust accordingly. So, like I said in the previous slide, whenever a local node detects a link cost change, it recalculates distance vectors, and then if its distance vector, and if that has changed, it notifies its neighbors. And through that mechanism, actually, that's all you need to make the shortest paths adjust themselves and converge to the correct solutions. Now, it turns out that when you have link costs go down, then it converges pretty quickly. And so the thing to remember is that good news travels quickly, and conversely, bad news does not travel quickly, at least in a shortest path distance vector routing algorithm. So like what will happen in this particular case, for example, is that, for example, if this node detects a change, it'll update its distance vector, it'll broadcast that to both x and y, and then z, for example, would realize now that it can reach x in not 5, but because y told it that y can reach x in 1, it can reach x in 2, so it'll update itself, and it's very straightforward and pretty quick. The more interesting case is when a node becomes more costly, and in that case, we say that bad news travels slowly. It'll still converge. The same thing will happen. Nodes will update their distance vectors and tell their neighbors, but there can be a very slow convergence. Like, for example, in this particular case, which the book goes through it in more detail, more slowly, but it'll actually take 44 steps for this algorithm to reconverge to the correct solution, even if it starts with the correct solution to the graph having 4 there instead of 60. And there's this sort of count to infinity problem where the values, the distances will go up in very small increments, because what happens is the two nodes, when they're talking to each other, will for example, when this one notices that the cost to here is 60, it doesn't want to use that link because it's very expensive. But it still has a record that Z thought from previously that it can get there in 5, so it'll actually try to route through Z. But even though Z's route originally of 5 was through Y, so that's not a useful thing to do. So Y will tell Z that, okay, I can get to X in 6, 1 plus 5, which is not at all true because it's still using the old information that this was 5. And Z will see that and say, okay, well, my best choice is not to go through 50, but to go through Y, because Y says I can get here in 6 steps. plus the 1 here is just 7. Okay, so I'll go through y and 7. And then y sees that, like, so you just have this small incrementing over and over again because they each are passing it back and forth to each other using old estimated distances. Yeah, which is pretty dumb. So the solution to this particular variation of this problem is what's called poisoned reverse, which means that you don't advertise to your neighbors that you can reach a node at all if the way that you reach it is through that neighbor. So that would solve this particular problem. So for example, when Z advertises to Y, when Z had advertised to Y before this change happened, it would not have even told Y that it can get to X in 5 steps, because the only way it can get to X is through Y, or the way it has chosen to go through get to X is through Y. So Z would actually tell Y that the cost for it to reach X is infinity, that it cannot reach X, therefore Y will not try to route through Z, because Z knows that the best way to get to X is through Y. Okay, a lot of letters. Yeah.
How exactly are the distance vectors like sent to node to node?
They are just like network messages. It's an application layer protocol.
Okay.
So the routers know each other's IP addresses, and they just communicate with the. I don't know offhand if it's like TCP or UDP, or like what the details are, but it's an application layer protocol. Okay. So that poison reverse solves that one count infinity problem, but actually you can still have something like that happen if you're using more than 2. If you have you can have a count to infinity that involves 3 or 4 or 5 nodes in a loop that are slowly incrementing their values. So this still can be a problem. Yeah.
So why does bad news spread slowly? Like, I see why all those things are problems.
Mm-hmm.
Why does it follow that like bad news in general travels slowly?
Well,
Or at least more slowly than good news?
Well, it follows the. I guess what's fundamentally different is that. So the problem with this distributed algorithm is that you're using old information from your neighbors, right? So in this case, Y was making an estimate of what it should route based on Z's old routing information, which didn't include the change. So if that old information includes a underestimate of the time, right? Because a link became faster. A link became slower. So old information is faster than is more optimistic about the distances. And it means, and you know that the purpose of this algorithm is to choose the shortest path, not the longest path. So if we're running a distributed longest path algorithm, then bad news would travel quickly and good news would travel slowly. But because we're actually the old news that tells us that there's this really fast link available, that actually it's not available anymore, will cause us to choose it, will cause us to make bad decisions. Whereas in the case of where we have old bad news, like we used to think that this was 4, but now it's 1, that old information that was pessimistic, I guess, about the distances will not cause us to, might cause us to ignore a route that's good, but it won't cause us to choose or to use a route that's bad. That makes some sense. That's the best I can explain. So yeah, because we're looking for shortest paths, old short paths do more harm than old longer paths. Okay. So to summarize these two approaches, if you think back, I mentioned Dijkstra's algorithm is a centralized link state algorithm that is faster overall. But it requires messages to be propagated, like it requires a complete information about the graph to be propagated to all the nodes ahead of time, which could be onerous. I didn't talk about it, but there are still convergence problems when a network is dynamic and you're using a centralized algorithm. You can have what are called oscillations in the solution. which is similar to the count to infinity problem. So I'm not sure one's better or the other in a dynamic situation. But I think the most important difference between centralized and distributed algorithms, of course, there's the feasibility aspect that you have to have control and you have to have trust in order to have a centralized algorithm. Like if you get information from your neighbors and your neighbors are hostile to you, and then they're in business competition with you, and they're so you can't necessarily trust the information they give you. Therefore, that's one reason why centralized algorithms are not used on the internet for the global routing on the internet. It's also true that the internet as a whole is too big to do everything centrally. But it's another important point is that somehow distributed algorithms are well, I'm not sure this is a very good point or a clear point, but centralized algorithms are more robust to a router failing. If there's one router that's not working correctly, I'll come to your questions in a second. What you'll have is incorrect link cost advertised to everyone else, and everyone else will perhaps calculate a route that includes bad link costs. But if you have, in distributed algorithm, one router that's malfunctioning and advertising bad information, that router could could attract a lot of traffic and become a sink. If that one router basically tells everyone that it has a great route to everywhere in the network, it can reach everywhere in 1 microsecond, then suddenly everyone will start routing the traffic to that one bad router and cause more havoc to everyone. So in some sense, a distributed algorithm is less robust to bad action. But then again, this is the kind of behavior that you probably wouldn't. It's not in this router's benefit to attract more traffic if it doesn't want to. But if it's malicious, it can cause problems. Do you have a question?
Yes. So the cost of the link between routers usually count both just normal link status and condition status.
So the cost can be really whatever you want it to be, depending on how you're using this algorithm. So far, I think I introduced this topic with the idea of doing shortest time routing, like shortest delay, so you'd use latency. But that's not the only thing you can use, because you can apply this to many different scenarios, as we'll see. So you could perhaps use the capacity of a link as a kind of cost, where a link that has less capacity has higher cost, because you don't want to overwhelm it. It could be that you're actually paying to use a link, so therefore you don't want to use a link because it will actually cost you money. Yeah, so it could be a variety of things. All right. Okay, so the kind of interesting thing about routing on the internet is that it's hierarchical and it happens at least 2 levels, which is maybe a bit of a surprise. So on the real internet, the routers are not all equal. They are divided into what are called autonomous systems. Okay, so the reason for this is that there are several reasons. First of all, there are too many routers on the internet, like hundreds of millions, to have them all in one big shortest path problem. Okay? That's one reason. Second reason is that every network operator would like to have some control over the routing that happens within their network. And like, for example, different operators may have agreements to peer with other ISPs for no cost, but then for other links they may have to pay for sending traffic on that link. And it could be that they want certain routers to be used more than others for other reasons. So what happens is you have the way the internet works is within every autonomous system there are routing protocols that run to determine how routing happens within that network. And then a different routing algorithm happens here to determine how routing works within this network. But then over the entire network as a whole, or the entire internet, there is one distributed algorithm used for every border gateway to decide which of the outside systems to send traffic to, which I hope that'll become more clear in the next few slides. Okay, so an autonomous system is a chunk of the internet that has its own like internally consistent routing policy, basically. But you can think of them as ISPs or organizations or parts of ISPs that maintain routing protocols within that system. So there are about 100,000 autonomous systems on the internet right now, maybe a little bit fewer. Everyone has an AS number, actually, that's distributed by the ICANN. That's sort of like an IP address, an address for the identifier for the AS. And these are generally ISPs or large organizations that are running groups of routers, right? And they have large blocks of IP addresses. And so you have two different types of routers now. You have gateway routers, which are the ones, or border gateways, which are the routers at the edge of the AS that connect to other ASs. And you have routers on the inside called interior gateways, or interior routers if you prefer. So the word gateway and router are sometimes used interchangeably. So BGP, the Border Gateway Protocol, is used by every single border gateway to communicate with other border gateways. That's standardized. That's a distributed algorithm. But then within the ASs, the different algorithms can be used at the whim of the operator of the AS. Okay. You got a question?
So you said at the beginning that the BGP uses Bellman-Ford.
Yeah.
So if Bellman-Ford is slower, why would it choose to use that over Dijkstra?
The reason is because Dijkstra's algorithm. So first of all, it doesn't really use Bellman-Ford directly. It uses kind of a simplification of it, and it doesn't use Dijkstra because there's no real way to implement it and get that efficiency without having information about the entire network. Whereas what we saw with Bellman-Ford and the distance vector routing algorithm in general is that you can make decisions just based on your neighbors and propagate that information to your neighbors, and eventually the whole system will converge after enough time, and that's what BGP does. So it's able to operate locally without having like this list. For Dijkstra's algorithm to really work, what makes it efficient is the fact that you have this list of visited nodes, and you sort the list of visited nodes according to distance from the source, and pick out the one that's closest. And if you have hundreds of millions of entries, you can't ever like really build that list in an efficient way. Okay. So in contrast to that, interior gateway protocols or intra-AS routing protocols are used within each AS. Right? So the network operator has control over their own routers, and they can run whatever algorithm they want to decide how traffic is routed between the various routers, and how the traffic from all the hosts connected to those routers is directed. So I only have like one slide to really address interior gateway protocols. There are 4 different protocols listed here. Open shortest path first, OSPF, ISIS. These are both basically Dijkstra's algorithm. And these are very common. Right? And the reason they're common is because Dijkstra's algorithm is really the best solution for a centralized shortest path problem. But there are also some interior gateway protocols that use a distributed distance vector approach as well. So these are similar to BGP, actually, but they're used internally. So one of them is the RIP, and then there's Cisco's Enhanced Interior Gateway Routing Protocol. But basically what happens here is that for these centralized algorithms, all these routers are configured by the same company. They agree to use a certain protocol, and then depending on the protocol, they have some way to gather information, to scatter and gather information, and therefore for each one to solve a shortest path problem. Okay. But I'm not going to go into details of those, because there are several of them that are all different, and I don't think it's terribly interesting. Okay. the open shortest path first algorithm. So by the way, the reason it's called open shortest path first, it's not the open shortest path, but it's open as an open source because this other algorithm was not, this other protocol is not like open documented. It's like a proprietary algorithm or protocol. So OSPF, one of the cool things about it is that it itself can be hierarchical. So you can actually have 3 levels of hierarchy. In internet routing, you can inside an AS you can actually have hierarchy, where the sort of backbone of the AS has a routing algorithm, and then the different subsections are divided into areas that run OSPF separately to solve several different shortest path problems, come up with routes there, and then just sort of an overall set of routes are determined at higher level. And then there are other details of OSPF, which are probably not terribly important, but there's authentication built into the algorithm. There is the ability to have multiple same cost paths, and you can have different link costs depending on the type of traffic, and make routing decisions that are not just based on IP address, but based on the either the ports being used or the IP flags indicate the type of traffic. All right. And in general, not just with OSPF, but with any intra-AS routing algorithm, you can always divide an AS into multiple private ASs. There's special reserved AS numbers that can be used internally, similar to how we have special private IP addresses that can be used internally, so you can actually run several AS algorithms internally. You could even run probably something like BGP to connect them internally. But at a higher level, and more interestingly, Border Gateway Protocol, or BGP, is used to kind of bind all these ASs together and decide how the sort of long-term, long-distance routes are constructed. So BGP is often called the glue that holds the internet together. And it's actually pretty simple if you understand the distance vector routing algorithm. That's what it uses. But there's some subtleties here in how do you map this to a shortest path problem to solve the distance vector. So instead of having nodes that we're trying to reach, like vertex numbers, we're trying to reach subnets. And instead of having weights or distances, we actually just use AS hop counts, the number of ASs you have to travel through to reach a destination as the weight. Okay, so BGP has 2 components, sort of external BGP and internal BGP. This is the main one up here. It's just the point is there's also an internal BGP protocol that's used to propagate. In order for this AS that has multiple routers to behave as one node in this larger algorithm, the nodes at the gateways and also the internal nodes have to share the information that they have. And that's what iBGP does. That's not really terribly interesting. You can just think of that as a algorithm that's used to share the information that's received by the various border gateways. But eBGP is really the main algorithm that figures out how to route among ASs. Yeah, question.
Just to be clear, like in this example, could you get to AS2 from AS2 to AS3 in 1, or like in 2 or 3 hops? Like does the routers in the AS count as a hop or no?
Well, so you'll see in the next couple slides the way that, from BGP's perspective, when calculating shortest paths, it sees the entire AS as like one unit.
Mm-hmm.
So this is like 2 hops. Is that your question?
Yeah.
So you actually, if this was a really large AS with lots of hops and lots of delay, like that wouldn't factor into the BGP algorithm, and so you might end up with a 4 choice. Okay, so the BGP routers, these exterior gateways, or border gateways, I should say, are the ones that participate in BGP, or at least in eBGP. These other ones interior nodes only participate in terms of getting updates from the exterior, from the border routers. And BGP sessions exist, which are just persistent connections between border gateways that have connectivity, and that's where they exchange distance vectors to update routing information for each other. So they're kind of in constant contact, exchanging distance vectors. Yeah, so like I said before, network prefixes are the things that each router is trying to find a shortest path to, not particular IP addresses or particular nodes. So it's not exactly a graph. It's not really a graph shortest path problem. I mean, it is that sort of graph shortest path problem, but every participant has a different view of the graph because from different gateways perspectives, different networks are aggregated into to larger networks. If that makes sense. So, for example, so network aggregation is important. That's when you take a series of IP addresses that actually form a contiguous chunk and kind of create a more succinct representation. So, for example, these are 4/24 subnets, or prefixes, I should say. They're not necessarily subnets. Prefixes that together form a /22 prefix, right? Because it's 0, 1, 2, and 3. Those are all that's changing is the lowest 2 bits, the bits number 23 and 24. So you can turn that into a /22. So when an AS advertises prefixes to its neighbors, and when it makes that advertisement, it basically tells its neighbor, I can reach these IP addresses, these prefixes, and not only can I reach those prefixes, but you can send your traffic through me to reach those prefixes. Okay, so those are what are called BGP advertisements. So border gateways are constantly sharing lists of BGP routes, which are like the distance vector elements in the distance vector. And I sort of simplified distance vector before. BGP routes are a little more complicated, but it's the same idea. What you have is a prefix, which basically indicates the destination. So, okay, I can reach this prefix, this block of IP addresses. The way I can reach that IP address is through this sequence of ASs. Okay, that's called the AS path. So it actually lists out the AS numbers through which that will be used to reach the destination. So if this advertisement is then used by someone else, by that receiver, to advertise this route to someone else, it would add its own AS to the beginning of the list. And then next hop indicates the IP address of the router that should receive is responsible for doing that forwarding. So, for example, if we're talking about AS3 that's doing an advertisement here, there could be a subnet here it can reach. Let's say it's this 20.1.0.0/22. It advertises that with this prefix. It says, okay, I can reach it in 3 hops. Here are the AS numbers, and the next hop is this IP address. The IP address of this particular router that will be is the one that should receive packets for that route. Okay, that's the next hop. So this is all it's saying is that, like, hey neighbor, you can send me traffic to this IP address range. If you send it to this router that's within my network, this is a border gateway, and when you do that, it'll go through 3 ASs, specifically these 3, to get there. So that whoever receives that message might turn around and add their own AS to this list of path, and then change the next hop to be an IP address of its own, whichever of its own border gateways it wants to use to do that routing. and which of its gateways it chooses would depend on the interior gateway routing algorithm that was run. Okay. So so all this says is how advertisements happen. It doesn't say anything about how the receivers of those advertisements react to them, and also how gateways decide which advertisements to make. Okay. So this slide kind of summarizes the rest of it, which is primarily, so this part here is BGP, really, and this first step is a way to sort of bypass BGP in some sense. But so like overall, I guess gateway route selection in practice goes as follows. So overall, an AS may have a local preference for a certain route. So in other words, the person who's configured the network may decide that, regardless of what anyone else says on the network, regardless of any BGP advertisements I receive, I always want to send traffic destined for a certain preface to this particular link, which is like this particular gateway. You may not always have these local preferences, but it could be that based on contracts that you have and the cost of using certain links, you have some local preference for sending traffic in certain directions. So that's just kind of like a built-in override that we can figure into our algorithm. But apart from that, the rest is controlled by BGP. So assuming that we're looking at a set of routes that have the same local preference, in other words, we've gotten past this step, we choose the route that has the shortest AS path. In other words, the shortest number of hops in this AS sequence, and that's based on the distance vector algorithm, based on the received route lists. We'll figure out how to calculate that. And then there's some tie breaking in these other steps. So if there are multiple paths that have the same number of ASs, then we use what's called hot potato routing, which is to use the route whose next hop is closest. So what this means is if your network looks like this, and you have a choice between using this next hop here and this next hop here, and the AS path is the same, local preference is the same. In other words, these both seem to get you to the destination in the same amount of time. Then what you do if you're a router here is figure out which one of these is closer. So in other words, if that's closer, I'll go this way. So for routers on this side of the network, we'll go this way. For routers on this side of the network, they'll go this way. If there's just one router right in your whole AS, then it'll be tied, if that makes sense. So hot potato routing is just the idea of getting the packet off your network as quickly as possible. So you don't care about what happens outside your network. In this case, what happens outside your network is tied anyway. So it makes sense to use a next decision criteria that's based only on local considerations, and you use the whatever is shortest in the based on your interior gateway protocol, like OSPF. You've run Dijkstra's algorithm locally to figure out the shortest paths locally to those nearby routers. And then if you still have a tie, you can use some other like random tiebreaker, which could be a BGP identifier, which is essentially just a number to identify each router. Okay. So how do we put those together? Let's see. So I talked about intra-AS routing algorithms, so within ASs. So these are like the Dijkstra style algorithms that are used inside these ASs to figure out what the shortest paths are and how, if I want to get from 1A to 1B, do I go all across this link or do I go through this one? And we also have algorithms working at a higher level to determine how to get to IP addresses that are outside the network. And both of those figure into the local forwarding tables that are stored at each router. Okay, so for local destinations, In other words, if for IP addresses that are inside your AS, then obviously you can just use whatever came out of the intra-AS routing algorithm, that OSPF, for example, Dijkstra's style algorithm that runs locally. And then for external destinations, you're going to eventually use the result of BGP. But in order to use that, you also have the first step of getting it to the edge. So you have to use a combination of these two, the outputs of both the algorithms. Because not only do BGP just tells you what the next hop is outside your network. Like, for example, send it to 2A or send it to 3A. But you still have to know the fastest way to get to those. And the way you do that is with the result of the intra-AS routing algorithms. All right. Okay, so I try to summarize this by asking, again, why we have two different routing algorithms. And several reasons. One of them is related to policy. So within an AS, administrators want to control how traffic is routed, and also which external routes are used. Sorry, this it's reverse. This is for inter-AS routing. In other words, like for BGP that's used between ISPs and other large organizations, the operator has control to advertise not just all the traffic, all the routes it has, but it actually can be selective and make I didn't mention that yet, but you have a choice. You can use policy to decide which advertisements you make. Like, for example, even though AS1 can reach AS3, it doesn't have to advertise that fact to AS3. It only does that. It only makes AS1 will only advertise a route to these IP addresses to AS2 if AS1 decides that it wants to allow AS2 to route through AS1 to get there. It doesn't have to do that. That depends on like business considerations, I guess. Like what kind of agreement it has with AS2, what kind of agreement it has with AS3, and whatever else. So the fact that BGP allows you to advertise selectively allows you to have some control over how traffic is routed and who routes through your network to reach outside networks. These intra-AS algorithms are within a single domain. They're centralized. So like when I described Dijkstra's algorithm, and I didn't really describe OSPF, but if you assume that OSPF works with a simple Dijkstra's algorithm implementation, then you'll see that there are no poly decisions built in. You just optimize for performance, which is here, right? But whereas between ASs, policy may be much more important than performance. So the fact that when you're configuring a BGP router, you have a lot of control over what you advertise, and that lets you implement different policies about who routes through you and where you send your traffic as well. And then another consideration, of course, was scale. So there are hundreds of millions of routers on the internet, and solving one big routing problem in a distributed way would not really be feasible. So hierarchical routing solves that problem, and BGP approaches this by doing AS hop level routing, which is kind of a very coarse way to figure out shortest path. But I want to say it works. It does. It seems to work. Yeah. All right. I guess that's all I have. So, sorry it was